Okay, everyone, let's get started. So this will be the last lecture with new material in it. In our next lecture, I'll just do a review for the final exam. Is that okay? Any problems with the project? Okay, so last time we were talking about CMOS logic, and I covered noise margins, which is the amount of noise you can tolerate on wires in order to, when you have noise affecting an already possibly noisy output from a driver gate, in order to avoid having the input go into the forbidden zone. And the forbidden zone is the voltage between what's considered a low voltage for the input, so that's VIL. So anything that's VIL or below is considered as logic 0. Anything that's VIH or above is a logic high for the input. And so the difference between VIL and VIH is fairly small. So there's a forbidden zone there that's fairly small because the way that the logic gates work is that the output voltage is or the forbidden zone for the output voltage is essentially much wider, because even if you give it of input voltage as high as VIL, the output for that is only, is not that high of a voltage compared to VIL. To make that sense. So in other words, the point is that there's a fairly small gap between VIL and VIH as compared to VOL and VOH. This is the logic 0 and logic 1 for the output for a gate. So if you have noise affecting a wire, you just have to keep the noise between below the difference of, for example, the VIL of this guy and the VOL of this guy, or conversely, you have to keep it between the VIH and VOH, right? Does that make sense? Okay, so that's the noise margin. Then we talked about semiconductors and transistor structures, and so this is the cross-sectional view of the NMOS and the PMOS, and the idea is that you've got a gate, a channel, and a source and drain. And then there's a fourth terminal, which is the body terminal, the bulk, that's the substrate underneath. And the idea is that you want to turn on the transistor, you charge, or you apply, in this case, a voltage to the gate. Now initially, the gate channel voltage is going to be, the channel's in this case is grounded, and so you basically have a capacitor here where you've got one terminal on the gate and another terminal is the substrate, the bulk. But what ends up happening after you start accumulating charge there, you get the minority charge carriers in the channel, which decouples the channel. It decouples the channel from the substrate, and so the voltage of the channel is no longer ground. The voltage of the channel is now, an average of the source and drain, because there's a connection there. So it becomes a little bit less straightforward to calculate the gate channel voltage. Okay, so then we talked about how you build CMOS gates. You have the pull-up network and the pull-down network. The pull-up network is PMOSs that turn on with a logic 0. And the pull-down network are NMOSs that turn on with a logic 1. And the two networks are complementary from one another. So for example, if you have the two PMOSs on the pull-up network in parallel, then the two NMOSs on the pull-down network should be in series. And then we talked about how in order to pull the output down to ground, you need to have at least one in the inputs. You need to have and that doesn't apply to this gate specifically, but in general, you have to be able to, in order to pull the output down to ground, you need to have at least one logic high on your input. And likewise, to pull the logic high, you need to have at least one logic 0. And that's just because the NMOSs are the pull down and the PMOSs are the pull up. So we looked at this is an AND gate and a NOR gate. And then we talked about transmission gates, which is where they're used for tri-state buffers. A transmission gate is a way to electrically disconnect two terminals. So we have an A terminal and a B terminal, and we want to be able to either connect them or disconnect them. So in that case, you'd have to use a PMOS and an NMOS in parallel, because that way, basically the PMOS is designed to carry a 0 across these terminals, and the NMOS is designed to carry the 1 across the terminals, right? Because, sorry, I had that reversed. Sorry. The PMOS carries the 1 and the NMOS carries the 0. Sorry, I had that wrong. Then we talked about power consumption, and there's dynamic power consumption is when you switch a gate from pulling down to pulling up, or from pulling up to pulling down, right? And so you've got like kind of a temporary short. You can estimate the dynamic power consumption as 1/2 capacitance times VDD squared times the switching frequency. And then static power consumption is a little less straightforward to calculate because that's the current that flows from power to the ground rail without the gate switching. So that's just the leakage current multiplied by the voltage. Okay, so we had an example of that, and then we switched back to talking about MOSFETs, and I mentioned that the thing to understand here, well, there's a couple things actually. So there's 3 operating regions. There's the cutoff region, which is where the transistor is turned off. That's when the gate voltage relative to in this case, the body, the substrate, is less than the threshold, which is usually like 700 millivolts or so. So that's the cutoff. That's when the transistor is off. Now, I mentioned that the static power consumption comes from the fact that even when it's off, there's still some current that can flow from source to drain, but very little. So when the transistor is in the cutoff, it will have basically a very high effective resistance. Now, when the gate voltage relative to the body hits the threshold, you go into, you turn the transistor on. Now, once it's on, it can be either in linear or saturation mode. But that depends not on what mode it's in doesn't depend on the gate voltage. What it depends on is the voltage drop between the source and drain. So in linear mode is when you have the transistor on, meaning that you have an inversion layer in the channel. So you have this inversion layer in the channel, meaning that the channel becomes decoupled from the body, and you start basically connecting the source and drain. And it's done through the charge carriers in the inversion region. So you have it on, and as you increase the voltage difference between the source and the drain, the current that flows through the transistor increases linearly, kind of linearly, right? Kind of like a resistor, right? So more voltage, you get more current. However, at a certain point, the problem is that you'll eventually, as you increase the source drain voltage, the gate channel voltage starts to get pinched off near the gate with the higher voltage. Sorry, near the terminal with the higher voltage. And the reason is again because the channel voltage is a gradient, right? From I mean, you have an average, it's average between the source and drain. Because remember, the source and drain, the channel is basically like a wire. You think of it as a wire, right? So if I put a big drop between these two guys, the voltage along that wire is going to start out at one side, and then it's going to gradually decrease until it hits the other side. Well, what that does is that takes the gate channel voltage towards the part with the higher voltage, and it sort of pinches it off, right? So you end up not having a big difference here between gate and channel on one side. And so when that happens, that's called the saturation mode, at which point the transistor will keep conducting current, but the current won't change even as you continue increasing the voltage. That's the saturation region. Make sense? You guys with me? So there's a limit on how much current we can send through the transistor. Okay, so then I derived the IV characteristics, but really the important point is here is that this equation gives the current, drain source current, as a function of the gate source and the drain source. And this is for the linear region. So, so basically the gate source minus the threshold voltage is one factor. And then the drain source is another. And then you have this beta, which is, it's a mixture between the carrier mobility mu and the capacitance of the oxide, which is that glass that's in between, that's underneath the gate. So these are technology dependent things. You can't change these. But then you have the width and the length. Those are not technology dependent. That's up to the designer. You can set the width and length to whatever you want it to be. Generally, the length is minimized. You want the length to be as small as possible. But the width is something you can change in order to, well, I mean, you can see, what is that doing exactly? If I increase the width, that increases this beta value, which is going to give me more current, right? So if you want more current, you can increase the width. Okay, so now once you hit the saturation region now, then the current is no longer a function of the drain source. The drain source voltage is out of the equation, and now it's only a function of VGS minus VT, the threshold, right? So cutoff is 0, although that's not entirely correct. That just assumes that's kind of a simplified model. 0 current for cutoff region. Linear region is, well, it's not really linear, right? It's because you got VDS squared here, right? And then the cutoff is just, it's when the transistor becomes a current source. Okay, so one thing you have to, so you can see that the linear region isn't, it's kind of linear, right? It looks kind of linear, right? This is the linear, so when the gate source voltage is 1.8 and you increase the drain source voltage, you start to, it increases kind of linearly and then it reaches the saturation point and it levels off, right? And then each of these curves depends on the gate source voltage. So you get different curves. So at 600 millivolts, you're basically in cutoff, right? This is the cutoff region because we're below the threshold here. So this line is flat, right? But at 0.9, which is just above the threshold, it looks like you saturate around 500 millivolts drain source or so. And then at 1.8, which is where you have it wide open, you saturate around 1.2 volts. And then so that's NMOS, and then PMOS. It's very similar, except these are negative voltages. Okay, does that make sense? Everyone clear on that? Okay, so one thing I want to mention here is Yeah, so where's my 3D? Oh, come on, I didn't delete that, did I? Yeah, here we go. Okay, so as I mentioned, the length, generally you want to have this length to be as short as possible. So this is the length is what you hear about when you hear like a 7 nanometer process or a 4 nanometer process. Now, as I mentioned, it used to be like if you had a 45 nanometer process or a 28 nanometer process, that was referring to this length, like the minimum feature size. Nowadays, when they say, I think Intel is down to a 4 nanometer, I mentioned that that's an equivalent. It's not actually, it's the technology, the fabrication technology node does not relate directly to this channel width, channel length anymore, right? It's more of an equivalency. And the reason is because there's just, I mean, at 4 nanometers, that's like, 8 atoms. That's really small, right? But the idea is that you want to make that channel as small as possible, because the smaller the channel is, the faster you get the charge carriers across the channel to carry the current. The width, on the other hand, is this dimension. And the width is generally you're going to adjust the width to make the transistor, you're going to get more current out of the transistor when you make it wider. Now, why would you want to do that? Why would you care about how much current you can get through the transistor? Now, you think about this, like, what is the transistor doing ultimately? It's driving the output of a logic gate, right? It's pulling down to ground or pulling up to VDD, right? And then that output is connected to inputs of other gates, and those inputs are connected to gates, right? And gates are capacitors, right? So capacitors, why would we want more current into a capacitor?
And more current drives your impedance down, I believe. So that means like whatever you're pushing through this resistor, you want to have more capacitance so you can keep your impedance down to power the rest of your circuit.
Well, the capacitor, so the capacitor is part of the gate's operation, right? And so when I have a gate and I switch from 0 to 1 or 1 to 0, what I'm really doing is charging or discharging the capacitors that are on the output of that gate, right? So, your outputs are connected to one of these guys, and so my goal is to charge up the capacitors that form the gates of my outputs, or to discharge them as fast as possible. And I can do that faster if I have more current, right? If I've got more current coming out of my either now there's two options here, right? Either you have more current coming from VDD down through your PMOSs out, right? Or you have more current coming back from the output gate down through my NMOSs down to ground. So either I'm sending current to my outputs through my PMOSs, or I'm sinking current back through my NMOSs, right? So either I'm pulling up, which means I'm charging up my load capacitors, or I'm discharging my load capacitors, right? The more current, and this only happens during a transition. Once it's discharged, then nothing. It's pretty much, but this is the dynamic power consumption part. So, yeah, it's basically the idea is that I'm charging up these gates, or I'm discharging. I need a lot of current to do that faster. So what that means is that if I want my circuit to be faster, I just make the transistors wider, right? So I can increase this width. By increasing that width, I can drive more capacitance faster. I can charge and discharge faster. So that's one of the things that one of the tricks you can play is usually the width is 5 times the length for an NMOS and 10 times the length for the PMOS, generally, right? So if this is a 45 nanometer length, then the width will be 450 nanometers if it's a PMOS, right? And half that for an NMOS, right? But that's the minimum size. I can make this a stronger transistor by widening it. If I widen it beyond the minimums, I still keep the length minimum, but if I widen it, I get more power. I get more drive strength, right? So, and you can see that in the equation. So hold on, if we go back to the so notice that the current is scaled by this beta term, and the length is in the denominator, right? So I want this to be, I want higher current. So I want this length to be minimized. I want this width to be, well, I can increase the width for more current, right? That's basically the idea. Okay. And that applies, by the way, to even to linear or saturation mode, either one, right? So even if I'm in saturation mode, which I probably will be right on a transition, right? Because think about it, like if I'm pulling up, I have a gate that's pulling up and its output is 1, and I want to switch it to 0. When I switch the pull down network on and the pull up network off, right after I do that, the voltage drop, my source drain voltage drop is basically going to be VDD. I'm going to start out with a heck of a voltage drop, right? Because I've got the output, the gates that I'm driving is 1, and I got to pull them down to 0. So I'm going to go into saturation mode almost instantly right after I transition, right? And so, but even in saturation mode, you still have that beta term, and remember, beta is, width over length, right? So then once I get it low enough, once I start to get that output down closer to 0, then I'll go into linear mode, right? And then I'll basically stay in linear mode, right? And then my pull-up network will be in cutoff mode, right? Okay. Okay. So I can make the width. I can increase the width, right? However, there is a consequence of doing that. The consequence of that is that if you make the width bigger, you also make the width of the channel bigger. You also make the width of the gate bigger, right? Now, I'm assuming we're doing this all uniformly, right? I mean, because I could make the width bigger on my driving gate, but I could keep it small on my downstream gate, the one on the output. But let's say I increase the widths all uniformly, all my gates. I make all my gates wider. What's going to happen is that I'm going to get more current, but the consequence of that is the area under this gate gets larger as well, right? And that increases the capacitance of the gate. So I kind of start working against myself because I get more current, but at the same time, I'm also increasing the capacitive load for the gate, right? And not only that, but the source and drain terminals, the source and drain diffusion area, they have to get wider. Their width is the same as the width of the channel, and it's impossible to tell that from that diagram. But if we look at that three-dimensional picture I've got, it's a little bit more obvious there. Yeah. So if you look at the three-dimensional picture, you can see that the source and drain will also get bigger. Their width is the same. Their width is the same as the gate width, right? And what happens there is they also are capacitors, because when you have a reverse biased diode, as you have here, like I ground, in this case, I ground the substrate, right? So this P is at a lower voltage than these two guys, which means that the diode that's formed from this P to this N is reverse biased, right? So they're not connected, even though they're, they're right up against each other. They're not connected electrically. However, they still form capacitors, right? Because a reverse bias diode is actually a capacitor, right? You might say, no, it's not. Capacitor is two conductors separated by an insulator. That's not what that is. Well, that's true, but a reverse bias diode does have an insulator. The insulator is the junction where the charge carriers move away from the junction in a reverse biasing. That becomes an insulator, effectively. The charge carriers, it's almost like, when the charge carriers move away from the junction because of the reverse biasing, because this is, this P is lower voltage than this N, right? So to send data through a diode, P has to be positive versus the N, but it's negative because it's a lower voltage than the N, right? So what ends up happening is that the charge carriers in this N get pushed away from the substrate, and the charge carriers in the substrate get pushed away. So because they get pushed away, it creates a kind of a dielectric. It becomes the middle of a capacitor, right? So as I make the transistor wider, I get a bigger capacitor here, I get a bigger capacitor here, and I get a bigger capacitor here, right? So I really get a lot more capacitance with wider transistors. So, well, first of all, how do you make wider transistors? So there's a couple ways to do it. There's a couple tricks. And so this will be a little bit confusing because I haven't shown much top-down pictures. I've showed the cutaway pictures. But this is, when you design a chip for manufacturing, it gets designed, the design looks like this because it's designed from the top, you're looking from the top down, right? And what you're seeing are these polygons, and each polygon represents a layer. So, what happens is that you can see that you've got there's a square here and a square here, right? These are source and drain diffusion areas. Okay. Actually, let me take that back. It's kind of hard to see, but it's actually this rectangle of gray. That's actually the diffusion area, right? And then these squares are actually contacts. And the contacts connect the diffusion area to a wire. The wires aren't actually shown here. I don't have the wires here. But you have to have a wire that goes down and touches the drain and the source. And that happens to these little black boxes. These are vias, right? And the square is actually metal around the via. So you have metal, via, which is a hole through the oxide, and then diffusion, right? So metal, hole, diffusion, right? So that's how I contact a wire down to the source and drain. And then this guy, this little horizontal piece, is polysilicon. That's the gate. You guys with me? You might say, wait, where's the glass? I thought you said there's supposed to be oxide. Yeah, the oxide is actually applied everywhere. It's actually, that wasn't shown in the cutaway very well. Let me clarify that. So notice how the oxide in this picture is just shown right there. That's actually not accurate. The oxide is everywhere. This oxide covers everything except where you have a contact. So there'll be a contact here, above here, that will be a hole of oxide, leave a hole of, the oxide there'll be a hole where there's no oxide, and then you put metal on top of there to actually connect a metal wire down, right? So this is a little misleading, this little gray area. It's not just under the gate. It's everywhere. It's everywhere you don't explicitly put a hole in the oxide. Does that make sense? Okay, so now you might say, wait a minute then, hold on. Then why is this gray? It looks like the diffusion area is under the gate, but it's not. It only looks that way. What ends up happening is that polysilicon is put down forget how they diffuse it. The diffusion area is not actually under that gate. I forget exactly how the steps are, but the way they deposit the layers on there when they fabricate, even though it looks like there's one continuous slab of diffusion, it's actually, this polysilicon layer actually blocks the diffusion underneath of it. Does that make sense? Okay, so what ends up happening is that the bottom line is that's the gate and this is the source and drain, right? But just looking from the top down, right? Now, if I want to make a wider, now, oh, by the way, too, the length is this part and the width is this part. See, it's labeled. You can see the width is labeled here. So the length is this is the width and this is the length, the vertical, right? The vertical size of this gate, right? Which would also be the length of the channel under the gate, right? Okay, so I can put two transistors in parallel. Here, right? You might say, how are those in parallel? Because the idea is that this gate would be connected. This would be one net. I would short these two gates, right? And so this side would go to VDD. This side would go to VDD, and the middle would go out, right? And so this would be essentially two gates in parallel. That's one thing you can do. Or you can take a shortcut where these two, instead of having a wire connected to the source and drain of these two guys, you could just have them overlapping with just one contact, right? That's more efficient. Or more efficient yet, you can literally create two parallel transistors just by having essentially two gates, right? Two gates on over one diffusion area. So that's isolated, shared, and merged diffusion regions. Oh, actually, these are in series in this case. Yeah, it's talking about putting these in series. Well, that works too if you have separate signals controlling these guys. Right. Okay. Okay. So, all right. So, why do we care about all these capacitances? Well, I mentioned this before, but the delay of a the CMOS circuit depends on the resistance and capacitance that's seen when you switch. And so it's kind of complicated because you can increase the strength of a gate, and you have to calculate basically the delay. So one simple way to do this is, and you can do this. I mean, obviously one way to do it is just run through SPICE. So in SPICE, you can have a transistor model there, and then you can set up these transistor level circuits in SPICE and run it. In that case, SPICE is going to have a model, transistor model, and that model is essentially what I showed you, or similar to what I showed you with the IV. This is the model. So the problem is that this model is not a linear model. So if you have a circuit, bless you, if you have a circuit in SPICE, you have to solve the circuit, like using Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law, right? But the problem is that these currents coming out through these transistors are not linear. There's no way to, I've heard that there's a way to model this linearly, or at least as a unified equation, instead of like having considering all three operating regions. It's called the Eber-Mols model. But SPICE just uses a model like this, that literally every transistor is in one of these three modes, depending on the drain source and this voltage saturation voltage. And so anyway, it's expensive. A simplified way to do it is to use an RC delay model. So if you consider a transistor, So you have a gate, drain, and source terminal. And if you consider the width of the transistor as K, so K is basically the number of minimal widths. So generally you have a minimal width, as I mentioned, it's going to be 5 times the length, the minimal length, right? And then if you want to make a bigger one, you can make a double size, a triple size, a quadruple size, right? And so that's K. It's just the number of widths, a multiple of the number of widths of the minimal width, right? And so that's going to basically determine your strength, your drive strength of that transistor. So if you consider that transistor just to be using a switch, like pretend it's a switch, then what happens is that the effective resistance is going to be the base resistance, the resistance of the minimal size transistor divided by K. So this way I can, if I make K2, then effectively I'm going to have my resistance, right? So the strength of the transistor is now basically a resistance value, right? Because basically, now, the transistor acts like a resistor in linear mode. In saturation mode, it doesn't. And that's why this is not a really super accurate model. But you could think of the transistor as having essentially an on resistance, is the idea. Does it make sense? Okay. And then you have 3 capacitors inside there. There's one capacitor that's the gate capacitance. And so any gate that drives this guy is going to see its gate capacitance. Then you have a capacitor from the source to ground and from the drain to ground. This is for an NMOS. You guys with me? Right? Why? Because the ground here is the substrate. It's the bulk. It's the body, right? It's the body is grounded for this guy. But remember, for a PMOS, it's the opposite. A PMOS has a capacitor for the source and drain, but it's to VDD because it's the well. Its substrate is VDD. Likewise, its gate is a capacitor to VDD as well. You guys with me? All right. Now the resistance, though, notice is 2RK. The reason for that is that in a PMOS transistor, the carriers have half the mobility of the carriers in an NMOS. So in almost every fabrication process, every cell library I've seen, or I should say every technology library I've seen, usually the width of the PMOSs are twice that as the NMOSs in order to create a balanced, in order to balance them. You guys with me? Okay, so now let's say you build a logic gate. So let's build an inverter. So an inverter is going to have a pull down and a pull up transistor. So we take the transistor model that I just showed you for both NMOS and PMOS, and we substitute them into the inverter, so we have the pull down and the pull up. You guys with me? Okay, so you got the inverter here, and then I'm going to have this inverter drive another inverter. Now you might say, well, why is that important? Well, in order to calculate the delay, you have to put a load on this guy. You can't just have an inverter and give a delay, because that delay is going to depend on what it's driving, what it's sending its output into. So we have to have two, in this case we have 2 inverters. We have A is the input to the first inverter, its output is Y, which is then fed into the input of the second inverter, right? Okay, so now the idea though is that on the first inverter, we don't have to look at the gate capacitance, right? We only look at the capacitance from the diffusion regions, right? The source and drain capacitance, basically, right? But on the second inverter that we're driving, then we have to only look at the gate capacitance. So you only care about the capacitance for the pull down and pull up transistors, source and drains, for the driving gate, but for the receiving gate, it's only the the gate capacitance. You guys with me? Okay? Okay, so what do you do with this then? Well, let's say I want to drive the output Y to 0, right? So what's going to happen there is the resistance is R to ground, right? Make sense? But I have one capacitor here. So what happens is what happens here is that on the bottom side of the pull down transistor, that's just grounded, right? So if you have source, I always forget, source is on top, drains on the bottom. I always forget that. For the NMOS, sorry, I always forget which one is which there. Yeah, so with the NMOS, its drain is on the top and source is on the bottom. So it's drain source, right? And on the PMOS, the source is on the top. So the source is going to be connected, to the ground, right? And the drain is going to be the output on an inverter. Okay, so if you look at this model, the drain is going to be connected to Y, the output, right? So we have to pay attention to this drain capacitance, right? The drain diffusion capacitance. The source we don't care about because you have a capacitor here, but both sides of this capacitor are grounded, right? So the source diffusionary capacitor, it's grounded, so we don't care. All we care about is this capacitance, right? This is the source capacitance, source diffusionary capacitance. Likewise, on the pull-up transistor, the source over here, this capacitor, again, is, look, both terminals of this guy are VDD, so we don't care about him. But if you look at the source capacitor, all right, this is now between Y and VDD. You guys see that? Okay, so what you end up with is if you simplify this, essentially what you have is a resistor that's connected to a capacitor to ground of C units of capacitance and a capacitor to VDD of 2C units. And you might say, why 2C? Well, because remember, the PMOSs have a K of 2 at the least, at the smallest. They have a 2, they're double size, right? The pull-up guys are double size because of the carrier mobility of the electrons is half of that of the holes. Make sense? Okay, but then also, that's just the driving side. Then the receiving side is this guy is going to drive two gates, right? There's the pull down gate and the pull up gate of the second gate, the second pair of transistors. And so this is the gate capacitance. So I've got another 2C capacitance on his pull up and C on his pull down. You guys with me? Okay? So what does this all mean? It means that the propagation delay of this first gate driving this second gate with K sizes listed here, 1 and 2, is going to be R times 6C, right? Because the delay is literally resistance times capacitance, right? Now, it's kind of weird because, you might say, well, wait a second. Some of these capacitors are connected to VDD and some are connected to ground. Why do you just lump them all into one? Well, because remember that I'm trying to discharge these capacitors, right? Well, I'm trying to charge the other two capacitors, right? So you're fighting against both sides. So it doesn't matter if you've got VDD or ground on the other side. What matters is that you're fighting all four of these capacitors. I'm fighting the source diffusion capacitor of my driving gate, and I'm fighting the gate capacitance of the driven gate, right? So you have to basically just add these up, right? Now you might say, well, wait a minute. What about, how do you calculate that in terms of seconds? So if you substitute in R and C values, you get seconds. This is literally seconds. The units are seconds. The capacitance, of course, would be farads. And you can get that. That's literally part of the technology parameters for your process. The resistance, though, is a little harder to come by. But if you simplify your model for this, you're going to associate a resistance value for your transistors. It's just an estimation, though, because remember, if you're in saturation mode, there's no resistance. You just get a constant amount of current. If you're in linear mode, there's kind of a resistance, because it's kind of linear, right? But so this is just a simplified model where I associate an R value with my transistor. You guys with me? Okay, all right. Okay, so now here's an example question. Consider an inverter whose PMOS widths are 2 minimal units, meaning K equals 2. And its NMOS widths are 1 minimal unit and driving 4 copies of itself. This is called the FO4 delay. FO standing for fan out, right? So this is a very common way to characterize a technology, a CMOS technology, FO4 delay. If you have a minimal size inverter driving 4 copies of itself, how long? What's the delay for that, right? But how would you calculate it with this model? Well, basically, it's the same thing we just did, except you're multiplying the load of the gate load by 4, right? So it's very simple. You just end up with R, and then you have 3 units of capacitance for the source capacitor for the PMOS and NMOS, and an additional 3 and then times 4, 12, right? So it's 3 plus 12 is 15. So RC times 15, right? You guys with me? So what is this? I mean, what are we talking like for this? I mean, what would it be for a modern chip? Picoseconds, 10 picoseconds, something like that, FO4 delay. Yeah. Something like that. Okay, so that was an inverter. Things get a little bit more complicated when you start considering more complex gates. So what if we look at a NAND? Okay, so the problem with the NAND gate is we have 3 PMOSs in series and 3 NMOSs, 3 PMOSs in parallel here, and 3 NMOSs in series. So it's a little bit more complicated. Not only that, but the delay actually is now going to depend, I think, on whether we're pulling up or down. It's no longer equal because of this. This is why we had before, remember we had propagation delay and contamination delay. This is one of the reasons why we have a difference between contamination delay and propagation. Because this guy, because he has these guys in parallel, he may be able to pull up faster than he can pull down, right? So the pull up time may be the contamination delay and the pull down will be the propagation delay, right? I think that's how it works out, but let's find out. So let's assume now that we size these guys with 3 and we size these with 2. You might say, wait, why would you do that? I thought you said the PMOSs are supposed to be bigger than the NMOSs. Well, yes, normally, yes, but the problem is that we have, these guys are in series, right? And so we want to reduce the resistance. We want these NMOSs to have lower resistance because they're in series, right? And when you have them in series, you're adding resistance. These guys are in parallel, so we can afford to keep them small and have relatively high resistance, right? Does it make sense? So that's how I've got these things sized. Okay, so yeah. So what do we do about that? Okay, well, so the problem here is that you have to replace each one of these transistors with our model, our RC model. And so the problem is you got to figure out which of these which drain capacitances can you eliminate? Now you might say, wait, in the inverter we eliminated all of them, right? But with this we can't, because I think we can eliminate them for these guys. For the pull-ups, I think you can get rid of the drain capacitance, because remember, you can get rid of any capacitor where both sides are at the same voltage, right? But the drain capacitors of the NMOSs, you can't get rid of those because they're connected in series, right? Okay, so let's. So what ends up happening here is we have, yeah. So like I said, so over here we have. So we have this guy, 2C. So this is a source capacitor here. So we got to get that source capacitor, and that source capacitor, and that source capacitor, right? So that's our output. So for this output, we have to consider those three source capacitors because they're all connected in parallel to the output wire, right? You guys with me? So that's 6C. Okay, but then we have this source capacitor is another 3 to ground. So we have 2, 4, 6, 9. 9C there. Okay? Right? That makes sense? So the output wire sees 9C of capacitance. Okay? Now, this drain capacitor can go away, just like these drains. These 3 drain capacitors go away. We don't care about them. This one goes away because he's grounded on both sides, right? However, this drain, these source capacitors, though, have to stay. So this source capacitor was accumulated into this 9, but this 3 and this 3 have to stay. They stay there, right? Make sense? You guys with me on that? And then, of course, the gate capacitance. So this first gate capacitor wire comes in, and he's going to see 3 units of capacitance for this gate, right? But he's also going to see another 2 on this gate. Remember, because every input is going to connect to 2 transistors, one in the pull-down network, one in the pull-up network, right? So this guy is going to see 5C because of the 3 for the pull-down transistor and 2 for the pull-up transistor. Okay? So this is the equivalent RC model. And again, basically all I did is I eliminated some of these redundant capacitors that were on the drains because they're both at the same voltage, and then combined other ones that were in parallel, right? That's it. That's all you do there, right? Okay, so the other thing you have to consider is that when you calculate an RC delay, it's assumed that you have a resistor and capacitor in series, right? In other words, you have a capacitor that you want to charge or discharge through a resistor, right? That's the RC delay. The problem is that this circuit is no longer that straightforward anymore because now you have branching paths where you have a wire that goes to a resistor and then a capacitor that goes to ground or VDD, but then another resistor and then another capacitor, right? You have a circuit where you've got lumps, right? You've got segments, right? With multiple resistors that are dividing up the circuit, essentially, right? So you have to use this approach called Elmore delay. Okay, so the Elmore delay it's a really simple idea. Basically, if you have something like this, where you have a signal, and you want to calculate how long it takes to switch this signal, right? The signal goes through a resistor and then through a capacitor, right? No problem. But then we have another resistor here, right? So the way that you have to calculate this delay, the time it takes to switch this guy over here, is going to be R1 times C, right? But then for this second capacitor, it's R1 plus R2 times C2. You add those two, right? Because this C2, this second capacitor, C is the resistance, the sum of these two resistors, right? So it's R1 times C plus R1 plus R2 times C2, right? So that's R1, R2, C2. Then R1 plus R2 plus R3 times C3, right? So that's the way, because you have to consider each capacitor, basically the time to charge or discharge each capacitor that's subject to all the resistances you see to get to that capacitor, right? If the resistors are in series like this. You guys make sense? Okay, so that's called Elmore delay. Okay, so if we want to estimate the worst case rising and falling delay of a 3-input NAND driving H identical gates. Okay, so we're going to go to the NAND. Okay, so the NAND is the same NAND we looked at before. So 2 units for the pull-ups, transistors, 3 units for the pull-down at the width, right? Okay, so we can calculate 2 propagation delays here. Propagation delay rising and propagation delay falling. Now remember when I covered timing closure or timing analysis, we only talked about propagation delay and contamination delay. But here we can further break it down into the rising and falling propagation delay. Does that make sense? Because we can calculate these separately. So for the rising, it's going to be the time it takes to pull the output up. So here's the circuit. We've got Y as our output, and we have we've got these. This is actually is this rising? Oh yeah, rising. So here's Y. So because we have these 3 guys in parallel, right? We only need one of them on, right, to pull up, right? Any one of those PMOSs turning on will pull up. So the resistance for the pull up there is basically just R, right? Why is it R? Because the size of the PMOSs is 2. When the PMOS size is 2, remember the delay is 2R divided by K. So if K is 2, it's just R, right? So R is our pull-up resistance, right? Then we've got Y, and we got some capacitance on Y. So how much capacitance? Well, basically, you have to add up the source capacitors of those 3 gates, pull-up gates, right? The diffusion capacitance. So that's going to be 2C, 2C, 2C. Those are 3 parallel capacitors, all with K equals 2. So that's going to be 6C, bless you. So I've got 6 units of capacitance for those source terminals, right? Okay? But then I also I'm driving H copies, so I've got the gate capacitance of the H copies, right? So what is H copies? Sorry, H identical. H is a variable, right? So what is the capacitance of the gates for this AND gate, for this NAND gate? Well, there's 3 inputs. Each input is driving 2 transistors. And then remember that there's the sizes are 2, 2, 2, 3, 3, 3. So the capacitance of the input, what is that? It's going to be, let's go back to the other diagram. It'd be easier that way. So the gates here are going to be, basically the capacitance is 2, 2, 2, 3, 3, 3, right? So it's going to be 4, and it's going to be, 6 plus 9, 15, right? 15 units in total. But that's all the inputs, right? So this AND gate is only going to be driving one of the inputs of those H copies of itself, right? It's not going to fan it out to all of them. That wouldn't make sense, right? So we're assuming that this output wire is going to connect to one of the 3 inputs of H copies. So for that, it's just 5, right? It's just 2 plus 3, because each input only goes to one pair of transistors, right? So it's 5, right? Okay, so yeah, so basically 5H, that's where we get the 5H comes from there, right? And then one thing I forgot about here was when you pull up, you're still going to get hit with, you've got the 6 units here of source capacitance, but you got to remember this guy too. The first NMOS in series has his source capacitance, which is 3, right? So it's going to be 2 plus 2 plus 2 plus 3, right? So it's going to be 6 plus 3 is 9, right? So you've got 9 units of capacitance on that node with diffusion area and 5 times H on the gates coming out. You guys with me? Make sense? So again, the 9C is the diffusion capacitance. The 5H is the gate capacitance of my load gate, assuming that that output just goes to one input on each of the 5 copies. Okay? Any questions about that? Make sense? Now that's just for pull up. Pull down is a little bit more complicated though, because the pull down has these 3 transistors in series, and this is where you have to use the Elmore delay. So the problem here is that if I want to pull down, I got to turn all 3 of these guys on, right? And so the delay here is going to be, from here pulling down, I'm going to have 3 units of capacitance here on this guy, right? I'm sorry. Yeah, 3 units here, this guy, right? Okay. And then the resistance of this guy is going to be R over 3, right? Because he's a bigger capacitor, a bigger transistor. So he has more capacitance but less resistance because he's wider. So it's R over 3. Then I have to add, so that's basically through this guy, right? So again, I've got a resistor capacitor, right? But then I have to go through this resistor to get to another resistor capacitor. So this is going to be 3C, which is this capacitor, the second one, but multiplied by R over 3 plus R over 3, because that's the resistance to get through these 2. You guys with me? Right? Then I have to do the same thing. Actually, I'm sorry, I started the wrong, I should have started at the bottom. This is the bottom one, actually. So 3C times R over 3, 3C times R over 3 plus R over 3. Then I get to this top guy, because again, you're calculating it relative to the ground, so we're working our way up. So we've got ground, 3C times this resistance, 3C plus this resistance, so going up here, right, from ground up to this transistor. And then finally, getting up to the top, I've got the 3 resistors in series, so I've got all 3 of these guys, right, R over 3 plus R over 3 plus R over 3. And then I'm going to multiply that by the 9, which is all the capacitance I have up at this node, plus 5HC, which is the load. Make sense? So initially, I was going the wrong direction. I was going down. You have to work your way up. So in this case, I'm working my way up from the ground through this resistor, that capacitor. Then through this resistor, that capacitor. Then through this resistor, this resistor, and then all these capacitors, right? Okay? So what's the difference? Well, this pull-up resistance is 9 plus 5H times RC. This one is 12 plus 5H plus RC. So even though I had bigger I had bigger transistors in the pull down. Because they were in series, my pull down propagation delay is higher than my pull up, right? My falling, PD falling, is actually higher than my PD rising. So you can see this is why, there's a difference between whether I'm pulling up or pulling down. Okay, so so I mentioned that the other thing too that might happen here, in addition to that, there's another phenomenon. What happens if all three inputs to this gate all go to 0 simultaneously? Right? So what's the difference? Well, what I was talking about before was I was assuming in this case that you see this R value in the pull-up? I was assuming there was only one of those pull-ups were on, right? Because there's only one R value here. You see that? See, there's one R, so I'm assuming only one of these guys is, and only one of them has to pull up. Because if any input is 0, then the NAND gate is going to give you a 1, right? But what happens, on the other hand, consider the case where all three inputs go to 0 at the same time. So all three of these pull-up transistors, they all turn on at the same time. So now I have less effective resistance on my pull-up. Make sense? So what's the pull-up there? It would be like having three of these R values in parallel. So that would just be, the 1 over R plus 1 over R plus 1 over R is my resistance, and then I multiply that by the same capacitance, right? So I have the same capacitance, but I have a lot less, less resistance, 1/3 the resistance. Make sense? So, that's really the contamination delay. The contamination delay isn't even this, because we saw that the pull-up time is faster, but that's even if just one pull-up turns on. If all three of them turn on, it's even faster yet, right? So this is, again, a difference between contamination and propagation delay. Okay, so the last thing I want to talk about is memory arrays. So we talked about memories already in class. Obviously you guys built memories on the FPGA, and we talked a little bit about the memories in the digital building blocks. Memories are basically when you have a 2D structure where you have depth, which is the number of entries in the array. You have an address input for that to address one of the entries. And then there's width, which is the number of bits you get out in parallel. Right? So there's different kinds of RAMs, of memory arrays. Dynamic random access memory, DRAM. Static random access memory is SRAM. So DRAM is like your main system memory. I'm sure you guys have heard of DRAM, right? And SRAM is when you have RAM that's on chip, that's like your cache that's on your CPU. And then, of course, there's a non-volatile flash memory. So whether you use DRAM or SRAM or flash RAM, they all work in a similar way. The memory is physically built as an array, as a 2D array of cells. The cells each store 1 bit. And so you have the 2D array has these wires that run horizontally and vertically. The horizontal wires are called the word lines, and the vertical wires are called the bit lines. And the word lines are how you write into the memory, and the bit lines are how you read from the memory, essentially. So for example, if your memory cell's word line is set, the bit line allows you to write into there, right? So you can write, for instance, a 0 in there or 1, right? Or alternatively, if the bit line is Z, high impedance, then it won't write, right? Now, how do you get Z? We'll use the transmission gate that we talked about earlier, PMOS, NMOS in parallel. You can turn it off and create a high impedance, right? You guys with me? Okay, so so basically what you end up with is an array where the number of rows of that array represent the depth of the RAM, and the number of columns is the width of the RAM. And so if you want to read you want to read a word, you need a decoder. So you send the address in the decoder, which converts from a binary to a unary representation where just one of the word lines is activated, right? And then that will, when the word line is activated, it'll connect the bit line to that word, to that row, right? And that allows you to read out, right? Now, when you do that, you would have to drive the bit line here, the input bit line, to high impedance because you wouldn't want to write to it, right? But if you do want to write to it, then you can set the bit lines and then you can just write into that word. You guys with me? Okay, so so in DRAM, the difference between DRAM and SRAM is basically how the cell is set up. So in DRAM, the cell in a DRAM is comprised of one transistor and one capacitor. So basically, the bit line, the word line is connected to the gate of the transistor, and it acts kind of like a pass gate, a transmission gate, even though there's only one transistor in there. And then the bit line allows you to, assuming the word line is active, if the bit line is grounded or set to VDD, it'll charge or discharge that capacitor. And that stores a bit, right? So every cell is just one transistor, one capacitor. That's how DRAM fundamentally works, right? Now that capacitor is always discharging, so you have to periodically refresh it even if you don't want to write it. Right? So in SRAM though, SRAM is no capacitor because you can't, in a CMOS technology, your whole goal is to minimize capacitance, right? And so you build the CMOS chips fundamentally, you fabricate them differently, so you can't have capacitors. So what instead you do is you create two inverters that are cross-coupled. Makes sense? So you got one inverter feeding another in a loop. So this will capture a bit. And then if you want to write in there, you have to set the bit line has to be 0, 1 or 1, 0. Or they could both be, high impedance if you don't want to write. But if you want to write, you would set these bit lines up. And then the word line will allow you, the word line is turned on, which allows the bits into the loop. And then the bit line will inject a bit, right, into this cross-coupled inverter. Does that make sense? So you can either put the bit line will be 0, 1 or 1, 0 that you'll use to then set the bit value in there. Does that make sense? Now, what's the difference here between the DRAM, the SRAM and the DRAM? The SRAM has two inverters, right? How many transistors are in an inverter? Remember, there's always two transistors per input, right? An inverter has one input, so there's two transistors here, and then you need two transistors here. So that's in total 6 transistors per bit, right? That's a SRAM cell is 6 transistors per bit just for the cells. That doesn't count the decoder for the word lines, right? The DRAM, on the other hand, is 1 transistor. 1 transistor per bit. Transistor, capacitor, that's it, right? So DRAM is much denser because it's costs less resources, which is why we still to this day use DRAM for the main system memory because DRAMs can be bigger, and they're fast. They're still fast. They're bigger. They're fast. The only problem with DRAM is they have to be on a different chip than your CPU because they're designed in a process that supports high capacitance, right? Whereas in an SRAM, a logic chip like your CPU, it's specifically designed to have minimal capacitance, right? Because that's what makes the logic slow, right? So we have this thing called the memory wall, which is the problem where you've got the CPU And you got your memory, and there's a bottleneck in between them because they're on different chips, and there's only so many wires you can connect them with. So any application that requires a lot of memory activity will end up having low utilization of the hardware on the CPU because you spend all your time waiting for the memory read and write. It's an unsolved problem. That's why people are looking at the in-memory computing technology. Okay, that's it. I think I timed that pretty well. That's all the content I have. So like I said, we'll review for the exam. If you have any questions about anything we covered all semester, you can bring those questions to the next lecture. And we might finish up early. The final exam is comprehensive, and it'll be given on Blackboard like the midterm. And like I said, you can if you're not confident about it or you don't even want to take it, then you can just do the final project.
And it's open all week like the midterm was?
Yes, it'll be open all week. It'll be 2 hours, just like the midterm. Okay? Yeah, and obviously there will be an emphasis on the stuff I covered later, because the stuff I covered earlier were designed for the practical parts for your CPU design, right? The later stuff was more conceptual, so that's more of the testing kind of stuff, right? So make sure you understand all the conceptual stuff. Okay.